introduce our session chair for this first paper session, Professor William Groski from University of Michigan, Dearborn, USA.
Oh, thank you, Frederick. It's nice to have an audience of your caliber here. So we're doing paper session 1. And if I had to characterize this session, I would say, you know, food computing or recipes meets data engineering is really like other areas that came before it in image interpretation and such. There's a lot of techniques that are used in all of these areas, including natural language processing. So in this session, we have 3 papers that use various approaches in food computing, you could say. Let me introduce the speaker of the first paper called Nutritional Profile Estimation in Cooking Recipes. So the speaker is Jushan Kalra, and he's a graduate student from the Department of Computer Engineering in Delhi Technological University in India. He's a student of a Professor Ganesh Bagler. And basically he's trying to extract information from a food artifact. It happens to be the nutritional component of the ingredients of that artifact. So, Jushan? Hello. Did anyone hear me?
I can hear you.
Okay, did you hear me before or?
Yes,
or
yes.
Okay, so is Jushan Kalra available there?
Yeah, but maybe he's having some issues.
Well, he's attending, but.
Yeah, he's here.
Okay. Well, we do have a backup just in case.
Yeah. Yes, we can pull out the.
Can somebody, okay. Yeah, I apologize for the speaker. He's having some problems with the mechanics here.
Yeah, we are trying to solve it.
He is in the room, but he may be having technical difficulties.
You will join.
Start the backup. I start the backup.
Oh, okay. Oh, his laptop crashed. Okay. Can you play the backup then, Frederick?
Yes, I start the backup.
Oh, don't forget, everyone, if you have questions, please write them on the chat and put the speaker's name too, please.
J'enlève mes... Vous voulez faire quoi? Je vais le faire en ordi. Ah, yes. Nutritional profile estimation in cooking recipes, please.
Hi, so the paper that we'll be discussing today is nutritional profile estimation in cooking recipes. So a little introduction about the paper. So it discusses a method to calculate the nutrition of the food that we eat. And we discuss why that is important in today's world and why it's important as a research topic, because it has a lot of applications in areas such as diet designing, recommendation systems, and dietary analytics. So in this paper, we use some natural language processing (NLP) techniques to calculate the composition of more than 100,000 recipes. So what is the problem in this? Why is this task so difficult? Why is this task that requires research? The reason is that, so if you look at the picture, you see there is one hard cooked egg, finely chopped, 1 tablespoon dill wheat, half teaspoon salt, freshly ground, and these things are not easily computable. So there is the need is to form this entire sentence into a structure so that it can be computed by a computer and then further computed to calculate the nutrition values. So how we did that was we created a custom NER system, a named entity recognition system that so we trained that model to recognize some tags, as you can see. So the model recognizes name, state, quantity, and unit primarily, with other tags as well. So all the sentences that we saw earlier on, so you can see that egg, hard cooked chop, quantity 1, all of them are segregated into different columns, and this makes it easier for us to compute these columns using computational techniques. So an important point about the NER that we made and used is that we used a bag of words approach, wherein we tagged all the words with the POS tagging, and POS tagging is part of speech tagging, and we clustered those and we made a vector of those tags, and then we clustered those vectors to get more diverse patterns, so that we don't miss out on some specific patterns that a custom NER does not recognize. So consider that we have our recipes in this form. What do we need now to actually compute the nutritional values? We need a nutritional database which has nutritional values corresponding to each ingredient. And there are a lot of nutritional composition tables, and a lot of them are mentioned on WHO. But the one that we went along with is the USDA, the United States Department of Agriculture's standard reference database, because it had a lot of ingredients, and because it had a lot of nutrients and a lot of accurate and a little better accuracy and a better review than the other composition tables that are present. And as we can see, so the USDA SR database had some so they had ingredients in the way as shown. So it had butter, salted butter, whipped with salt, butter without salt, cheese blue. So it had a lot of different ingredients, and some of them are very similar, which plays a role later on. But it's very diverse. So that is why we went along with this nutritional data set. So the first job that we have to do after getting the result from the NER is to match the ingredient names that we have acquired with the food description that is present in the USDA database. And that is an interesting problem which we solved by Jaccard similarity. So I'll talk more about Jaccard similarity in the next few slides. But just as an example, we can see that if the ingredient name was Roma tomato, and the food description that we matched was soup, tomato, beef with noodle, canned, condensed. Now, obviously, this is not that accurate, but it's the best that we got from our nutrition data set. If you look at coriander, if you got that in recipe, it would be matched to coriander, cilantro leaves, raw, which is pretty accurate. So there are two types of Jaccard indexes mentioned here, the vanilla type and the modified type, and we'll be talking about that in the next few slides. But the basic takeaway is that you need to match the ingredients that are coming in recipes with the nutrition composition table, and that is done using the Jaccard index. So to accurately map those food descriptions in the standard reference database, we look for some patterns in the food description streams that are generally present and that are generally prevalent in nutrition composition tables. So the first takeaway was that descriptions in the USD SR database are comma separated terms with a decreasing degree of importance. So generally it's like, if you can see the C point, it's egg, white, raw, fresh. So egg is the most important part. That is the part that we have to match first, and then white, and then raw, and then fresh. So yeah, so USDA has comma separated terms with a decreasing degree of importance. The high priority terms include both singular and plural forms of nouns, and they have to be lemmatized before matching. For this, we use the NLTK library for lemmatization. Yeah, so if you see the C point, the ingredient name egg whites best matches with the description egg white raw fresh, whereas whole eggs best match egg whole raw fresh. The sequence of terms may be different in both the strings being considered. And this is the primary reason that we use Jaccard index as a metric for similarity, because Jaccard index does not care about where the word comes in the string. It only cares about if the word is same or not. It's basically the intersection upon the union, as we'll discuss in the next slide. So the normal vanilla Jaccard is basically the intersection of two strings, number of words that match in two strings upon the union of the number of words in both the strings. But this posed a problem in the sense we wanted to prioritize the mapping of maxim terms from the ingredient phrase rather than the food description that was present in the USDA. For example, if you have some recipes that are sourced from that a person has written, so you will more likely write egg white instead of egg white raw fresh. So it's more important to match the ingredient description that is coming from a food recipe rather than the one that we have in the nutrition composition tables. So to accommodate to us, and because of that, if we had actually not considered this, what was happening was that the denominator in Jaccard distance increases with the increasing sizing of one of the strings. So what this leads to is a bias against large strings. But since it's only essential to match the maximum number of terms from the ingredient phrase, we used the modulus of A, that is the size of A, as the denominator for a Jaccard index instead of A union B. And we show in the paper that this definitely results in a better accuracy than the vanilla Jaccard. And actually, you can see it in these examples that if you have red lentils, then it matches better than the modified Jaccard index matches better than the vanilla one. Yeah, so the validity of the Jaccard index. So we had to verify that our results that we were getting from the Jaccard index were correct or not. So for that, we collected the top 5,000 most frequent ingredients in our data set of more than 100,000 recipes. And we manually checked it against the USD dataset, and out of which 3,580 were deemed to be correct matches, and the rest had a better match available in the dataset. So this results in an accuracy of 71.6%. An important side note here is that USDA, as we discussed before, has a lot of similar ingredients with little variation. So while Jaccard similarity does not always give the best match, it almost always gives one of the suitable matches from a database. So if I will go back and show you one example here, we had butter, salted. We had butter, salted and butter, whipped with salt. These don't really, they won't differ a lot in terms of their nutrition values, and so it's fine if we match either of them. So that is what was happening because of the Jaccard similarity, because there were multiple matches which could have been deemed correct, but those who manually matched with the USG dataset thought that they were wrong. So anyway, so we achieved an accuracy of 71.6% in the Jaccard index. So after matching our ingredient, what else do we require to get the nutrition value? So if we have one tablespoon of butter, then we have the entire information that we need to calculate that ingredient's nutrition value. So now that we have that, till now we've just matched butter. So what we need to do is we need to map the unit that we have in our database and the unit that is presented in the recipe, and we need to match the amount that is present in both. So So what we did was we scaled the available nutritional information for standard 100 grams in the USDA database based on the quantity in units. And this task is not as easy as it seems first, because the USDA dataset is not complete. In the sense, it does not have all units for all ingredients. So, for example, in this example only, if you see butter, salted, teaspoon is not present as unit, even though it may be used in some recipes. And so to accommodate this, we use some measurement conversion tables and cleaning techniques, because these units that you see here are already clean, but they were in the nutrition composition table, they were present in the form, for example, pat, bracket, and it was 1/3 inches and so on. And instead of TBSP, the short form tablespoon, it was complete tablespoon. And this created a problem, because if in a recipe we have complete tablespoon written, and in the composition table we have the short form tablespoon written, that poses a problem. So we had to standardize the data across board and say, yeah, so tablespoon and its short form refer to the same unit, and we had to depict that, and so do pound. So those are two examples out of many. And yeah, so after cleaning and unit matching, after we get the correct unit, so now we have that that entire information that we require to calculate one ingredient's nutrition value. That is, that we have 1 tablespoon of butter, and then we know how much nutrition it has. We'll be able to calculate how much nutrition it has. So yeah, so this is the overall system architecture that we use. So as you can see, the first point is we've used an NER model to segregate the information into ingredient name, processing state, freshness information, temperature, and so on and so forth, and the quantitative information, which is quantity in units. And then we use the hierarchical string similarity match with the priority based string matching, and we used the so we used Jaccard similarity to match strings. And once we got the correct ingredient, we used our quantity and units and their matching to get the correct amount that of that ingredient in the recipe, so that we will be able to compute it. And then it was a simple matter of manipulating the data present in the nutrition composition table to get the final nutrition information. Right. So so this graph gives us an idea of what the percentage of mapping of our recipes is. So as we can see, so 90 to 100% ingredients get mapped in only 5% of the recipes, which shows that there is some problem either in the Jaccard similarity index, wherein a lot of ingredients are not getting matched with a certain threshold, and or there is a problem in the unit matching, which is also occurring because the USDA does not have all units, right? So if it does not have if it does not have cup and tablespoon and teaspoon all together, all three of them, then it's difficult to match the correct unit. If it just has, if for example, if a recipe says one chicken, we probably wouldn't be having a matching ingredient in the nutrition composition table. They generally have these units in terms of pounds and so on and so forth. So these are the limitations that we have, and most of them are related to the nutrition composition table, which is why we see that not more than 5% get completely mapped, and most of the recipes have 60 to 70% of the ingredients matched. So once we have those ingredients matched, it's to get the final nutrition profile of the recipe, we added them up. So for example, if it has 10 ingredients, and we have for each ingredient we have its nutrition profile, the nutrition profile from this heuristic. So the nutrition of the recipe is just the total sum of those individual ingredients. And an important question to be raised here is, why isn't yield values considered, and why aren't cooking methodologies considered? And that is something that needs to be worked on. But since there is no since there is no good source of field values, and there has been research done wherein where it has been stated that these cooking methodologies do not change nutrition values by a significant degree, and we see that in our computations. But yes, so they don't mention a threshold. It was just theoretical study, but that has been quoted in the paper. Yeah, so once we match those ingredients and once we add them up, we get the final nutrition values. So to evaluate our heuristics, so we considered all recipes, which is a website, nutrition data as the gold standard for the evaluation. We selected data for which we had 100% mapping of ingredients with the nutrition values and had clean, well-defined servings present. So this resulted in around 2,500 recipes, and this was done. We only took 100% mapping because our recipe dataset has a global coverage, right, spanning like almost the entire world. Like those 100,000 recipes come from various regions, and the nutrition composition table that we used as a sample is only US-based model. And even though it has a lot of ingredients, it is missing out on some key ingredients that may be regional specific. For example, garam masala, which is a spice used in Indian dishes, is not an ingredient present in the dataset. And it's used in a lot of recipes, and that creates a problem because that ingredient will not get matched. So because of these region-centric ingredients, some ingredients will not match. And we observed an average per serving error of 36.42 calories for the recipes with 100% ingredient matching. So yeah, that was pretty much, that was it. And if you have any questions, I'll see you guys in the Q&A section.
All right, thank you. I assume that was a recording, Frederick, or not?
Yes, it was recording. Yes, thank you.
Okay. Okay, so we have some time. I think there was one question here, but maybe he'll be able to come to the latter meeting that we have this afternoon and answer it. So why don't we go on? So the second talk is concerning basically issues in data modeling. It's a talk called A Named Entity-Based Approach to Model Recipes. The speaker is Devansh Batra. He's a graduate student of the Department of Information Technology, Netaji Subhas University of Technology in New Delhi, India. He's a student of Professor Ganesh Baglar. Is he here? Yes, hi. Hi, Devansh. So can somebody unmute him? Or unmute.
Hello.
Yeah. Hi, Devansh.
Hi. So, hello, my name is Devansh Batra. This is a presentation for the paper titled Named Entity-Based Approach to Model Recipes. This work was done at the Inference Institute of Information Technology, New Delhi, at the Complex System Labs, which is supervised by Dr. Ganesh Baglar. As an introduction, one of the goals of natural language processing is understanding. And we know it is very hard to give a definition to understanding for general texts. Traditionally, recipes have been represented as belonging to the paradigm of instructional language, which I will deal with later, which basically comprise of step-by-step instructions to be performed in order to complete a task. So traditionally, there have been graph-based methods which have been used for modeling a cooking recipe. The first one of which was very popular for its time, is by using flow graphs. So this was introduced by Shinsuke Mori et al. At the first workshop on cooking with computers. In the paper title is A Machine Learning Approach to Recipe Text Processing. So as you can see, the flow graphs depend on relationships between the entities that occur within the instructions. Graph-based approaches have been popular in this context because they allow capturing interactive relationships within the various entities. After gradual evolution of these representations, we see a highly sophisticated and specialized approach, well thought out for cooking recipes themselves. It was introduced in EMNLP in 2015. By the way, by Mesa and class, unsupervised interpretation of instructional recipes. You can see an input recipe on the left and a partial corresponding output action graph on the right. The leftmost oval in each action is the action's verb, and the following ovals, Aij, represent the verb's arguments. The yellow oval represents foods, the gray oval represents locations, arguments. Argument oval with dotted boundaries are also present. You can read more about this representation in the paper mentioned. But this was specifically focused on cooking recipes themselves, and there were some very interesting results for different applications which were presented in the paper. Apart from these, there are also some word sequence based models which have been previously used to model recipes, but they also largely only focus on instructions section. So we can consider this as another family of models which is present in the literature, and they do not rely on relationship between word pairs, but instead on their co-occurrence in a particular order. There are three major types of approaches which have been taken in literature using word-based sequence model: the general bag of words model, which most of us would be familiar with, a sentence bag of words model, where the temporary vocabulary is limited to the sentence, and subsequent sentence bag of words model, which does not employ the whole recipe text at an instant, but only a subset of it. And it was found that for searching based problems or applications in cooking recipes, that is like giving complex search queries. For example, I want to search a recipe which belongs to a certain cuisine and uses a certain ingredient and has certain utensils which I have available. So the flow graph based method which was presented in the earlier slide by Shinsuke Mori et al. Clearly outclassed all of these word sequence based models when it was first introduced, which can be seen by graph based models have been focused on in the recent years. So what are the use cases of these recipe models? Uh, there can be many, and some of them have been written on this slide. I've also shown some of the applications of our model in subsequent slides, but largely there would be more intelligent recipe search, which was explained in the previous slide, assistance for cooking by using observed features of human behaviors, automatic alignment of cooking videos and recipe flow graphs, and automatic cooking machines. But there are certain issues associated with these approaches. So both the graph-based representations mentioned so far, along with other similar approaches, acknowledge that the ingredient section is a fundamental part of the representation of a cooking recipe. The figure on the left is taken from the paper Shinsuke Mori et al. They do acknowledge that the ingredient section is an integral part of the text, but they do not pay any heed to it when it comes to actual data modeling. And this can be fatal for applications which uh, deal with quantitative information of ingredient. As you can see in the recipe on the left, there is no quantitative information which is referenced within the instruction section. The quantitative information, by which I mean how much of an ingredient is present, is only present in the ingredient section. You cannot tell how many hot dogs were actually cooked from the instruction section, or what would be their nutritional estimation, because much of it depends upon the quantity or the amount, or maybe the percentage of it, which cannot be derived from instruction section. So applications such as food pairing, flavor prediction, nutritional estimation, cost estimation, and cuisine prediction do face problems with these approaches. So ingredient section, let us try to define what an ingredient section actually is. It should be very clear from the previous slide. This can be seen as an unordered list of phrases detailing quantitative information, ingredient name, state. By state here I mean something like minced, rolled, diced, etc., which is going to significantly affect the amount of ingredient that is going to be used. And there is some temperature information, something is cold, something is hot, which can affect the way different ingredients behave together while cooking. And some dryness information, whether something is dry or fresh, and other miscellaneous details. It is important to note that these are not grammatical sentences. They do not follow grammatical rules which we see in general language, which can be expected from instruction section. So we present an integrated modeling framework which pays the due credence that the ingredient section deserves. In order to fully capture the required information, we train a special named entity recognition model. It has been explained in the later slides. A part of it was also featured in the previous presentation, which relies largely on this model. We model the instruction section as a temporal sequence of events, which are relationships between ingredients, processes, and utensils. This is very similar to the graph-based approaches or the relationship-based approaches which were explained in the previous slides. And we train another named entity recognition model to extract relationships and using grammatical rules for the instruction section. I would like to give some idea about recipe DB. Recipe DB, which was also mentioned by Jushan, is the dataset we have used for this purpose. You can go to the website and see all of the data and the model explanation which has been mentioned in these papers. So there are 1,18,000 recipes or 118,000 recipes available on which we have done our experiments. So what do we expect from ingredient section? We need a formal definition of the entities which should be accepted. As detailed before, we require the name, which would be used to actually identify the ingredient, state, quantity, unit, temperature, dryness or freshness state, and the size. Size is basically alternative to quantity. But if someone says, I need a medium hot dog versus one hot dogs, and so size may be present when unit and quantity are not. But there are certain challenges that we need to pay heed to. There are three types of challenges. The first one is corpus of attributes. This is probably because this is the first attempt to actually model the ingredient section. There is no known corpus which can identify all ingredients or all processing states in different cooking techniques, because recipes by nature are constantly evolving and new ingredients and new cooking techniques keep coming up. So we cannot rely on a fixed corpus to learn all of the representations. And even if we do, they are going to evolve over time. Identification of attributes. So attributes may be homographs. A club may refer to the ingredient itself, or it may refer to the unit of measurement. For example, a club of cheese. These here club means two very different things. Variation in lexical structure of ingredient phrases. There exists a huge variation in the lexical structure of writing an ingredient phrase. So if someone tries a parsing based approach, that may not work very well, because you can see there are simple and complex type of ingredient phrases which have been explained here. 3/4 cup of sugar, which is relatively simple, versus something like 1 packaged cream cheese, which could also be read as 8 ounces of packaged cream cheese, and softened would be steak. Now I explain how we actually went about finding the entities which were represented before. First of all, we tagged the entire corpus of recipe DB using the Stanford POS Tagger, and this gave us word vectors corresponding to each ingredient phrase, which give us the frequency of the POS tags present. The Stanford POS Tagger supports 36 POS tags, so the vector output would be a 1 cross 36 vector output for each of the phrase, where each value in the vector corresponds to a POS tag. So, for example, in the POS tagged output above, the vector below here represents that there is one instance of the CC tag, two instances of NN tags, and so forth. Now, this vector can be used as the feature input to find similarities. We apply some clustering based approaches, the K-means clustering and spherical K-means clustering, and using them we identify unique clusters. So they display similar structure of the ingredient phrase because they are clustered based on the POS tags present, which takes the grammatical structure into account. And for all of these clusters which were identified, we took 1% of the ingredient phrases to form the training set and 0.33% of the ingredient phrases to form the test set. We have explained the sizes of the three corpora which were formed, the old recipes, food.com, and a combination of these recipes. All of this is available within the recipe DB database. Now I will explain about the actual name entity recognition model which was used to find the entities. The entities have been explained here once again, which were also done in the previous slide. So there are 7 entities which have been found out using the Stanford NER tagger. The link is here in the slide. You can refer to the paper as well for a better understanding of the significance of each of these entities. But again, name would be used to identify the recipe, unit quantity, and the size would give us some quantitative information. State, temperature, and dryness of refrigeration state would affect the way the ingredients interact with each other. This slide basically tells the performance which we found our NER tagger to give. It can be seen that when we mix the all recipes in food.com corpus, here all recipes has recipes from several different cuisines, whereas food.com focuses largely on American cuisine. So we found that it is far better to actually merge both the corpus for training and testing purposes to have a better effort score. And you can easily see we have a consistent F1 scores of about 0.95 or above in all of the possible corpus combinations. Now that's it for the ingredient section. For modeling the instruction section, there could be various approaches used, but I'll explain what we have done. So first of all, we found all the required entities. In this case, the entities would be processes, utensils, and ingredients within the instruction section. We train an NER model using a similar pipeline as described in the previous slides to find all the processes, ingredients, and utensils within the recipe. You can see the dataset sizes in the paper. We also filter the ingredients to only include the ingredients mentioned within the ingredient section. We'll see why we do this in the later slide. However, since this may or may not be essential depending upon the use case of the project, we share the evaluation of the NER model for processes and utensils only. Because, well, you may or may not want to have the output of ingredient entities which are not listed specifically within the ingredient section. For example, something when two ingredients are mixed, they may form a mixture. And a lot of times our model said a mixture was an ingredient when that was not listed in the ingredient section. So what if an ingredient came out of elsewhere and it was an optional ingredient, so it was not mentioned in the ingredient section, that would be labeled as an ingredient. So we have filtered those out. Again, in this case, you can see we have a decent F1 score of about 90%. For processing and utensils, we observed a similar score for ingredients. So let us look at this recipe. This is the inference of the NER model on our recipe. I'm not sure if you can see my mouse, but if you see over here, mixture and patties, these are like two of the ingredients which would not be present within the ingredient section of the recipe, and which is why we actually filtered them out. This may or may not be required based on the use case or the application of for which our algorithm is being used. So rule-based event extraction. Uh, we use a modified version of the algorithm detailed in the paper cited below from the International Conference on Information and Knowledge Engineering. We found out all the verbs using POS tagging. We found out the entities and verbs which were associated with it in the same dependency tree to find the tuples of relations, and these tuples were used for further processing. So the pipeline would be to actually detect the verbs after NER has been performed using uh, POS tagging, and then finding the entities, the ingredients, and the utensils associated with these processes, which were believed to be more or less given by the verbs, to find the relationship tuples. But there is a special requirement which we have for this purpose, the need for many-to-many relationships. This can be better understood with an example. An instruction may state that potatoes are boiled. It may also state that potatoes are fried with olive oil in a pan. In this case, the relation extends to both the ingredients olive oil and potatoes as well as the utensil pan. So you can see the same verb or the same process actually represents two different relationship tuples. So we can say that olive oil, potatoes, and pan, all of them are being uh, subjected to the same process. So this is what we mean by many-to-many relationships over here. For further clarification, please refer to the paper. And here is a trivial example from an inference. This is actually the inference of the relationship tuples from the recipes shown over here. If you look at the first line, bring a large pot of lightly salted water to a boil. You will see that both water and pot are associated with the process bring. So that is what we meant by many-to-many relations, which have been successfully mapped using this approach. And now applications. So the recipe DB has a dedicated website where we have uh, actually used this model for several applications. One of them is the similarity of recipes. We have found a recipe similar to a given recipe on the basis of several different parameters which could be uh, gathered by using the language model which we just described, and nutritional estimation which was explained by Jushan in the preceding presentation. So in conclusion, we provide a novel way to model recipes which gives due credence to ingredient section, unlike the previous models available in literature. We explain the challenges involved and our reasoning behind the choice of entities in our NER-based approach for ingredient section. We evaluate the utilization of name entity recognition model, achieving F1 scores of 95% and 90% in the ingredient section and instruction section respectively. And the proposed model has been utilized in recipe DB for the applications explained in the previous slide. We also present a similar model for instruction section, which heavily depends upon both NER and relationship exception. So there is scope for future work in this approach, and we list out some of the things that could be tried out by the fellow researchers, like finding patterns of co-occurrence or proofs of evolution of cuisines. So my friends Utkarsh, Tript, and Jushan have actually tried this, and this would be available in the next session. They use the model reference explained here. Also, these models can be helpful in finding novel cooking combinations and novel recipes which are not known yet. We are actively working on a project involving generation of novel cooking recipes by trying to predict the relationships which would be found in the instruction section while keeping in sync with the information from the ingredient section. Similarly, a model which incorporate both ingredient section and instruction section more coherently, that is, they use the same data engineering techniques and not two different ones to model them. That would make it easier for use in development and research. So that's it. If you have any question, feel free to answer.
Okay. Thank you very much. Thank you. So, okay, our questions again, make sure you get them on the chat for later. And we'll go on to our third paper. I would characterize this paper as an embeddings paper for downstream applications, as they say in NLP. So basically, well, the title of the paper is Food Recipe, Alternation and Generation with Natural Language Processing Techniques, and the author is Changwen Xu from Fordham University. He's a grad student from the Department of Computer and Information Sciences over there. And Fordham is either in the Bronx or Manhattan. It's probably in the Bronx, New York City area. So he's under the supervision of a Dr. Yanjun Lee. So I think he's here as well.
Yeah, I'm here and
Okay, good.
to deal with the share screen.
Yeah, go ahead. Can you share the screen? Go ahead.
Yeah, give me seconds. Let's see.
Okay.
Now you can see my screen.
No, I see something that says you. Yeah, it's coming. Yeah.
Okay. Shall I begin?
Yeah, everything's fine, I think. Go ahead.
Yeah. Hi, ladies and gentlemen. I'm Changwen. Today, I'm here to introduce you some interesting results and findings about my research project, Food Recipe Iteration and Generation with Natural Language Processing Techniques. Before coming into our project, let me ask you some questions. If there are only 20 food ingredients in the world, how many recipes could we humanity create with them? You could use 2, 3, 4, or even all of them. Take a guess. The total number is over 1 million. It's simple math. Just add up all combinations from 2 of 20, 3 of 20, along towards 20 of 20. Then you got this huge number. Then, do you know how many meals you may have in your whole life? Assuming that we will all be long-lived enough to be 100 years old, when we would have had still less than 0.1 million meals. In other words, you need to live 10 times to try all possible food recipes, even if there are only 20 ingredients options. As an individual, I can never have enough time or appetite to know if I like certain dish. And there are some more reality conditions. Imagine that when you want to make a great dish at home, but one of the ingredients is out of stock. The closest grocery store is like 5 miles away? Do you want to know what could you use to replace of the missing one? Or this question could be, you are doing a special new diet due to some healthy reason. For example, ketogenic. Could you make a ketogenic version lasagna since it was your favorite? If we can find some patterns or rules of creating recipes, it will also be very useful in our real daily life. With those rules found, many problems like this could be easily solved. By implementing word embedding models, we could measure the similarity between words in text. Assuming that two similar words could be swapped without changing the meaning of original text, we could use the similar ingredients word to replace the original one. Furthermore, by calculating the similarity between recipes, we could know how much alike they are. Then it's possible to find the substitute of certain dish. Besides,
you have a problem with the slides. Can you update your sharing screen? It seems you have a problem. Sorry.
You cannot see my screen?
You move, but it was not moving to the next slide. Sorry to disturb.
Okay, it's okay. I'll try to fix it. Okay, let me continue my presentation. Besides, we build language models to generate new recipes with authentic flavor of certain cuisine style. To compare and improve the performance, some popular deep learning models are used, including RNN and LSTM. With those models, we can quickly generate new recipes with several given beginning words. To implement those models, Python packages were adopted, and the recipes data are collected from a website called Spunkula, which also provides recipes information for many communities and model apps. After removing duplicates, we collect about 3,400 recipes across 15 different cuisine styles all around the world, like French, Chinese, Japanese, Thai, Germany, and something so on. Okay, to preprocess the recipe dataset, we perform the traditional NLP techniques like tokenization, steaming, and stop words removal. We also manually merge some ingredients of subtype into a more general type. For example, merging different kinds of tomato, like Romania tomato, plum tomato, to one certain ingredients tomato. That will make our analysis more general. And besides, to improve the training, we perform the part of speech tagging in the cooking instruction steps. Only keep the verbs and nouns. The exact amount of each ingredients in the recipes were also ignored, like the 15 grams or like 1 ounce. Those numbers were ignored in our similarity analysis. We made some additional steps like pair cooking process and ingredients relatively. For example, we have brown rice cooked, or garlic minced, or chicken tender chopped. It specifies the process of cooking, help us search for similar recipes more accurately. Before coming to the modeling, we wish to know more about our dataset. We started the ingredient distribution of each cuisine style. American style has the highest number of ingredients. It's about 683. And Africa style has the lowest number, 364. The average number of ingredients of 15 cuisine style is 519. To observe ingredients frequency in each cuisine style, we create word clouds to visualize them. Common ingredients such as salt, olive oil, and garlic are generally used here. And you can see this picture for the results. The size of the word indicates the frequency of this ingredient. The visualization shows that we could easily tell the cuisine style based on the frequently used ingredients with common cooking knowledge. Here is like small test of that. There are 4 different word clouds. Based on those word clouds, we can take a guess which cuisine style is coming from. It's pretty simple actually. We can see the result here. The first one is Chinese. You can see in Chinese cuisine, they use the soy sauce, sesame oil, and for the Italian, the Parmesan cheese. And they love the canned tomatoes. And the Indian food here, the onions and the garlic powder, ginger are most commonly used. And for the Vietnamese, the fish sauce, lime juice, they are very different, and we can see some different usage of the ingredients in different culture. To study the shared common ingredients across 15 cuisine styles, we create a list of top 20 frequent ingredients of each cuisine style, and then compare with each other to get the shared ingredients between cuisines. More shared ingredients indicate that those 2 cuisine styles are more related. The maximum of shared ingredients is 16 between the pair of Italian and the Mediterranean. Japanese and the Korea shared 15 ingredients. Chinese and Japanese, also French and the Mediterranean both shared 14 ingredients. Those findings are not surprising since, those cuisine styles are well known to be similar. But here is an interesting finding that Indian and the African shared 14 among top 20 ingredients. The next style is Thai against the Vietnamese and the American against the German. They both shared 12 ingredients. The least shared ingredients number is only 1. That's between the pair of Vietnamese and the German. This finding shows that the Vietnamese is the least related to Germany. And in such a special social distancing time, having your dinner in restaurants has been a daydream. Cooking on your own becomes an unbeatable option. Then preparing the grocery for cooking is very struggling, or even struggling since it's tough to get out for just a tomato. You will always miss something, but don't worry, there might be an alternative at your home. To help find this alternative, we used the word embedding here. Word2vec package of Genism model was adopted to implement the scheme-gram algorithm with negative sampling. In theorem, word embedding vector with larger dimension store more information. And usually it sits between 300 and 500. We have tested several settings and found that there was no big difference for this project. Maybe it's caused by the volume of our dataset. So the dimensionality of word embedding was set as 100. The training was performed on the whole dataset. Each ingredient was represented with one embedding vector of 100 dimension. But here's a question. To find the alternative ingredient for a recipe when required one is not available. Our initial intuition is choosing the most similar ingredient as a substitute. The ingredient similarity was measured with the cosine similarity of their ingredients embedding. However, the similarity measured based on scheme-gram algorithm sometimes it only reflects that the two words are similar because they often show up together in the same context. In the other words in the same context neighborhood are also considered similar, but they might not to be good alternative for each other. For example here, turkey bacon and eggs both have great similarity with bacon, but you can say only turkey bacon could be a reasonable substitute for it. The result in table shows the findings of alternative ingredients across all cuisine styles with different window size and training epochs. We could say, with different parameter setting when training, the final models do give various suggestions. To avoid the problem we just mentioned, that show up together but not similar problem, we could use smaller window size setting, but meanwhile, smaller window size may perform not as good as larger ones. It's basically a trade-off. And in actual operations, you don't need to treat the suggestion given by models as final guide. We can also take our human knowledge into consideration to determine if the substitute is reasonable. Our interesting finding is calamari is found as the substitute of carrot in all cases here. Maybe I should try it next time. Okay. Besides that, when making the word embedding inside each cuisine style, not the whole dataset, the results vary. It's easy to understand since different cuisines have widely different usage of certain same ingredients. You will see some interesting findings here. They do reflect how those people innovate their food. It may not be so accurate or ground truth, but provide some inspiration. Let's pay attention to the alternative for onion. In Chinese cuisine style, it could be usually replaced by curry powder. Based on that, we may be able to conclude that Chinese cuisines often use onions as just condiments, but not a to-eat part. And for French, it becomes firstly, the usage is actually similar to Chinese, I think. However, while we come to American cuisine, it returns to tomato paste. Looks like the American people enjoy the flavor of mixing onion and tomato, so that they always put them together. And for Mediterranean, that becomes zucchini. Either they just love cooking onions as vegetable, or they take the sweet flavor of onion to make the zucchini taste better. Since we can replace some ingredients when cooking, can we replace the whole recipe? Of course, yes. When directly building the models on instruction text, it didn't perform very well. Then we think a recipe is defined by its ingredients and the corresponding cooking steps. Words except those two things could be considered as noise. So in the preprocessing step, we extract the ingredients and the process pair and build our model based on this to avoid the noise from other unrelated words. The intuition of measuring similarity of two recipes is to study the overlapping between two recipes. Doc2Vec package of Journalism module was adopted to obtain the recipe embedding. So, instead of ingredient embedding, each recipe was represented by its document embedding. In other words, the ingredient process embedding. To train this model with skip-gram algorithm with negative samples, we set the parameter kind of differently to give more weight to those low-frequency words. It's easy to understand. The common steps like chopping garlic or heat olive oil they cannot determine the style of recipe because, you know, a lot of recipe, a lot of dishes would have these steps. Only the uncommon steps, like heat to melt the chocolate or stir-fried dished chicken thigh, they are the key part we want to value. Let me give some example here. To find the most similar recipe to tomato beef lasagna, which is a very common Italian dish. When searching the whole dataset across 15 cuisine styles, the top results are those. The firstly, Greek tomato beef lasagna from Mediterranean. I think they two are basically the same thing with just some minor difference in seasoning. That makes sense. And the second one is, I don't know how to exactly spell this name, but it's basically made of wine, chicken, potato, mushroom, and whatever vegetable you like. And the third one is brunch egg burritos from Mexico. Okay, I think they are both kind of tortillas and stuffing. By comparing recipes embedding similarity, we could search for similar recipes from different cuisine or from different diet catalogs. Stir-fried potato beef lasagna, the most like American recipe for it is turkey tetrazzini, which I believe is spaghetti with chopped turkey and a lot of cheese. That's pretty American, right? Of course, we can try it in specified diet catalog. There is a Vietnamese dish called bong cha. Actually, it's rice thin noodle with meatball topping. If you are gluten-free but still want to have similar dish, you could try Vietnamese beef stew, North African fish soup, or fish soup, or Thai seafood salad. They are made from as similar ingredients and the cooking methods as possible, but you know, without any gluten. And here is another 3 vegan version of this dish. Okay, end of similar thing story. Let's create something new. We want to generate brand new recipes based on learning old ones. To build a recipe generator, we first trained the traditional n-gram language model, where n equals to 3 on the dataset. Cooking instructions of all recipes from the same cuisine styles was concatenated to create one document as the training dataset. Since the amount of each ingredient was ignored during the embedding training, the new recipes do not have specific amount of each ingredient. Here are 2 recipe samples generated with max 50 tokens by feeding heat the water. Since n-gram model performs the greedy search for next word with highest probability, and it has no backoff mechanism, the generated text begins to repeat part of the process and it's stuck in a loop. That is absolutely not satisfying. Therefore, we tried some more powerful deep learning models, LSTM, which was implemented to perform a mini batch training or sequences of 10 tokens. The training datasets kept the original format of recipes without doing any traditional NLP preprocessing, except the tokenization. The original recipes were not trimmed and the digits were not removed. Recipes were grouped according to each cuisine style, concatenated as a long sequence of texts. as the training dataset. The sample results of generated recipes with given inputs through cooking until rice is heated through and the pews are just cooked to serve with. Here are the results. And you can have a simple look at this. We made some statistics about our generations. On average, recipes generated by 3-gram model include 5 recognizable cooking steps and 3 ingredients. And those generated by LSTM model include 7 recognizable cooking steps and 8 ingredients. That's pretty better. Based on the evaluation of 6 volunteers, the generated cooking instruction with LSTM did extract some important process and ingredients of each cuisine. In the future, we plan to implement RNN model to say if it will perform better. But before that, we need to collect more recipes since RNN is good at large datasets. Our 3,400 recipes is far away from enough. Okay, that's my presentation today. Thank you, guys.
So, thank you, Cheng-Wen. Okay, so we will, I think we will end the morning session here. But don't forget, if you have any questions, just put them on the chat now, please.
Yeah, I will answer questions now.
Yeah. We can answer all the questions in our afternoon session, or if anybody has a question now, I guess. Well, okay. So we'll do it this afternoon, and so that's it. So the next session is our second keynote, and that starts at 1:30 Dallas time, Central Time, which is an hour before Eastern Time. So see you guys then. Thank you very much.
Thank you.
Oh, well, that's nice.